So we're just going to do a quick problem describing the rotational energy and doing a derivation to figure out what the final velocity of this disk that's rolling down a slope is going to be. So this is just going to practice kind of setting up an energy problem, but also like some kind of complex and involved substitutions that we're going to have to make as we go through here. So the start of the problem is actually pretty easy. We're trying to find what the final velocity at the bottom is. And so to do that, we'll just start with describing this with an energy bar chart. We can say at the beginning, we have gravitational potential energy. And at the end, we're going to have some translational kinetic energy and some rotational kinetic energy. So when I set up my my energy problem at the very beginning, I'm going to try and do this in separate colors. Hopefully it doesn't get super obnoxious to do it that way, but I'll do blue for my rotational or my translational kinetic energy, and I'll try and do red for my rotational kinetic energy. We'll see if I need other colors as we go through here. So as this is the energy equation that we start with, gravitational turning into both forms of kinetic energy as we go down. We're going to be trying to solve for V, so let's start plugging in some of our variables right away. We have something that looks like mg. It's the equation here is mg delta y from your formula sheet, but I'm going to write mgl because L is my change in height that's happening here. And I'll just put a plus there for later. For rotational kinetic, or for translational kinetic energy, it's 1/2 mv squared. And the m is given to me, so I'm going to turn this into a capital M just so it matches the variables that are given to us in the problem. This is the v that we're going to be trying to solve for eventually. I guess if I'm doing capital M, I need to do this as capital M there as well. All right, and then the rotational kinetic energy is going to be 1/2 I omega squared. But you can see right now that I have a little bit of an issue because I have 1, 2, 3, 4, 5, 6, 7. I have like so many different letters that represent so many different things that if I was to just try and solve it in terms of V right now, I'm going to end up with this like disgusting mishmash of different variables. And probably what they're going to ask you guys for if this comes up is they're going to say solve it in terms of M and R and M, R, and L, the variables that we gave you, not anything else. So we're going to start doing some substitutions. We're going to do a substitution for the rotational inertia. And if this was given to you guys as a problem, this would be told to you guys. You would be told, since this is a disk, the rotational inertia is equal to 1/2 mr squared. So that's not something that you have to have memorized, but that would be part of the problem given to you is 1/2 mr squared. But that tells us, okay, we are going to have to plug that in. So when we plug that in, that's going to be plus 1/2 times the rotational inertia, pulling that in, 1/2 mr squared. And I should use capital M and capital R because those are the variables that were given to us right there. And then I'm going to multiply that by omega squared. But omega is, again, one of those variables we're not allowed to have. So let's do a substitution there as well. This substitution you guys need to know to make on your own. Where we know I've taught you guys, we've learned that as long as it's not slipping down the slope, the linear velocity is equal to r times the angular velocity. So I can rewrite that as v over r equals omega. And now I have something that I can plug in there in place of omega. So I'm going to plug that in. That's going to be 1/2 times the rotational inertia, 1/2 mr squared, times v over r. I'm going to make that a capital so it matches the variable here again. And then I have to square that because the omega is being squared. So this is pretty ugly right now. So I'm going to simplify it real quick. Notice that there's a 1/2 and a 1/2 here. So if I multiply those two halves together, I'm going to get 1/4. And then notice that this square here has to be distributed. So that's going to be v squared and r squared. But that puts an r squared in the bottom and an r squared in the top. So those actually end up canceling out. So by the time I'm done, I actually have 1/4 mv squared. And then I still have this 1/2 mv squared. Oops, this should really be a capital M. Shame on me. 1/2 mv squared. And that all equals this mgl that we started with. So looking at where we're at now, I should use a different color. Notice that there's a mass term in every single one of these. So that mass term is going to cancel. And this leads to kind of an important fact that, as usual, mass still doesn't matter. Whether we're doing this with just something sliding down the slope or we're dealing with something rolling down the slope, the mass already canceled. And if you notice here, the radius actually didn't matter either. The radius also canceled. So the radius doesn't matter either. All right, so now that we've got those in there, let's keep doing our simplifying work. GL equals 1/2 v squared plus 1/4 v squared. At this point, I have to combine them. So we'll just go with purple because, red plus blue. And 1/2 plus 1/4 equals 3/4. V squared equals GL. Oops. GL. And if I'm trying to get V by itself, it'll work out that V equals 4/3 GL square rooted if we just solve for V. So that's how you do the derivation. But notice, again, interestingly, the radius of this thing ended up canceling. The mass of this thing ended up canceling. But we did get a different result than we would have if it had been just a block going down. If you recall, a block sliding down, the problem that we've done a million times, a million different ways, it works out to be 2GL, or the square root of 2GL. And so that's the final takeaway that I want you guys to have here, is what actually does matter. And this half is what made all the difference in the world. While the radius doesn't matter and the mass doesn't matter, the shape matters. So the more rotational inertia that the shape is going to have, the bigger this term ends up being, and therefore the more the slower it ends up going at the end. So if this had been a disk, like I believe we're doing in class, if this had ended up being a disk, we end up with mr squared. So we would end up with even more rotational kinetic energy and therefore an even lower velocity. If we had done this with a sphere, which has the formula 2/5 mr squared, then we would end up with even less rotational kinetic energy, which means we'd have more linear kinetic energy or translational kinetic energy, and therefore a faster speed at the end. So there we go. There is the derivation that you would do. Notice, of course, that the rotational side got kind of messy because there were a lot of things that we plugged in and canceled. But there you go. Now you should know how to do rotational energy problems. Thanks for watching.